Hello everyone. Today we are going to discuss about improvement methods of simple VCR cycle. So in this video you are going to learn about the different improvement methods for the simple VCR saturation cycle. So there are four different methods available for the improvement of simple VCR system. So one of that is using flash chamber between expansion valve and the evaporator. Another one is the using accumulator or pre-cooler. Third one is by subcooling of the liquid refrigerant by vapor refrigerant. And fourth one is subcooling of the liquid refrigerant leaving the condenser by liquid refrigerant from the expansion valve. So throughout this video you will going to see how these methods are useful for the improvement of the simple VCR cycle. So first one is simple saturation cycle with the flash chamber. Here you can see that in simple VCR cycle there is a flash chamber attached inside the system after expansion valve and before the evaporator. So we have already discussed when high pressure liquid refrigerant from the condenser passes through the expansion valve, then partial evaporation of liquid refrigerant is occurred. So that partial evaporation of liquid refrigerant is known as the flash. So the vapor which is generated during the expansion, that is known as flash, and removal of that flash is occurs inside the flash chamber, as this flash is no use in the evaporator, as it is not going to produce the refrigerating effect because it has no ability to absorb the heat. So additional equipment that is known as flash chamber is attached into the cycle. So the whatever is liquid refrigerant coming from the expansion valve evaporated and converted to the flash is directly transferred to the compressor, and only the liquid is transferred to the evaporator. So the benefit of using it is that the cooling effect produced inside the evaporator will be higher. So the system has not to do more work. The flash chamber is an insulated container and it separates the liquid and vapor due to centrifugal effect. So the mass of the refrigerant passing through the evaporator reduces. So now consider that a certain amount of refrigerant is circulating through the condenser. This refrigerant after passing through the expansion valve is supplied to the flash chamber, which separates the liquid and vapor refrigerant. The vapor is directly transferred to the compressor and liquid is transferred to the evaporator. So the pH chart of this system is like this. Here the mass M1, that is the mass of liquid refrigerant supplied to the evaporator, and mass M2. M2 is the total mass of the refrigerant that is passing through the condenser or leaving from the expansion valve, and M2 minus M1 is the mass of flash that is directly transferred to the compressor. Now for the analysis of the system, first we have to do heat balance. So the heat taken by the flash chamber is equal to heat given out by the flash chamber. So heat taken by the flash chamber, that is M2H4. Here we can see that at the point 4 M2 mass is entering into the flash chamber. M1 mass is leaving from the flash chamber, that is transferred to evaporator, and M2 minus M1, that is mass of flash, that is transferred to the compressor. So M2 minus H4, that is equal to M1 HF4 dash plus M2 minus M1 into H1. So M1 HF4 dash means the liquid that is transferred to evaporator, and M2 minus M1 into H1, that is transferred to the compressor. So again separating M2 and M1, we are having M2 H1 minus H4 and M1 H1 minus H4 HF4 dash. So from that we are having the equation for M1, that is M2 H1 minus H4 by H1 minus HF4 dash. Also H4 is equal to HF3, so H4 can be replaced by HF3. Here you can see inside the pH chart, that is 4 and 3 enthalpy is same. So the refrigerating effect is M1 H1 minus HF4 dash, and replacing the value for M1 from this equation. So we are having the equation of RE, that is equal to M2 H1 minus HF3. Work done to the compressor, that is M2 H2 minus H1. Remember here in work done we have to take M2, because compressor has to work with the whole amount of refrigerant, while inside the evaporator only M1 mass is transferred. So in refrigerating effect only M1 is there, and for work done M2 is there. So power can be calculated by W by 60. So M2 H2 minus H1 by 60 kilowatt, and as we know COP is RE by W, so it is H1 minus HF3 divided by H2 minus H1. So this way we can find out the COP of the system. So the coefficient of performance and the power required are same as that of the simple saturation cycle when the flash chamber is not in use. Thus the use of flash chamber has no effect on the thermodynamic cycle. The only effect resulting from the use of flash chamber is the reduction in mass of refrigerant flowing through the evaporator. Here we can see that only mass M1 is transferred. So reduction of the size of evaporator. So that is the benefit of this simple saturation cycle while using the flash chamber. So the benefit of this is reduction in mass and reduction in size of evaporator. Now the second one, the second system for the improvement used is accumulator. Use of accumulator, or we can say pre-cooler. It is also known as pre-cooler. So here we can see that in between compressor and evaporator and expansion valve and evaporator, there is a device which is known as accumulator. So sometimes the liquid refrigerant passing through the evaporator is not completely evaporated, as we have already discussed in previous video that in actual cycle whatever the refrigerant is leaving the evaporator, somewhat amount of refrigerant is in liquid state. So if the compressor has is supplied with liquid along with the vapor refrigerant, then the compressor has to do an additional work of evaporating and raising the temperature of liquid refrigerant. So normal working of compressor will not be there. So in order to avoid this difficulty, an insulated vessel known as accumulator or pre-cooler is installed between the compressor and evaporator. The discharge from the evaporator is directly sent to the accumulator, which helps to keep off the liquid from entering the compressor. So whatever the refrigerant coming out from the evaporator is directly transferred to accumulator, which is going to mix with the liquid refrigerant which is coming from the expansion valve. Here this accumulator also works as a flush chamber. So the amount of flush which is generated after the expansion, that also be removed, and only liquid is transferred to the evaporator. So the flash, or we can say vapor, that is generated is directly transferred to the compressor. So here the mass m1 is the mass of liquid refrigerant circulating through evaporator, as we have seen in previous modification with the flash chamber. Same, and m2 is the mass of refrigerant that is moving from the compressor and condenser, that is m2. Now here again the pH chart is nearly same as a simple VCR cycle. So heat taken by the accumulator and heat given out by the accumulator. So heat balance, so m2h4 plus m1h1 dash. Here we can see that here m2 is entering and m2 is rejecting, and here m1 is exiting and m1 is entering. So liquid plus vapor, that is m1, that is entering inside the accumulator after evaporator, and m1 amount of liquid is transferred to the evaporator. Same as total mass, that is m2 entering to the accumulator after expansion valve, and m2 in vapor form. So total mass m2 in vapor form, that is transferred to the compressor. So m2h4 plus m1h1 dash is equal to m2h1 plus m1hf4 dash. So here from this we can find out the equation for m1, and again hf4 h4 is equal to hf3, as we can see inside the pH chart. So that can be written here. So same as refrigerating effect, that is m1 h1 dash minus hf4 dash. Here check out the difference between these two. Here for this with flash chamber we are having h1 only. So in refrigerating effect, here it is h1 minus hf4 dash, but in this case we are having h1 dash. So this is the point where the liquid is enter to the exiting to the evaporator. So refrigerating effect is m1 h1 dash minus hf4 dash. So ultimately Re is equal to m2 h1 minus hf3, and same as W is equal to m2 h2 minus h1. Here the difference between these two system with using flash chamber and with accumulator is that in refrigerating effect the m2 same m1 mass need to be transferred. So okay, COP is Re by W, and we are having h1 minus hf3 and divided by h2 minus h1, that is the final COP of the system. So here also the coefficient of the performance and power required is same as simple saturation cycle. So the benefit of this using of accumulator is the only to protect the liquid refrigerant to flow into the compressor, and thus dry compression is always ensured, and there is a benefit of no failure of the system by compressing the liquid refrigerant. So only dry saturated vapor is transferred inside the compressor. So that is the main benefit of the system. So another modification, that is subcooling of the liquid refrigerant by vapor refrigerant. So here a heat exchanger is produced between the lines. So the one of the portion is between condenser and expansion valve, and another portion that is evaporator and compressor. So here we can see that a heat exchanger in between the system is provided. So as we know that the liquid refrigerant leaving the condenser is at higher temperature than the vapor refrigerant leaving the evaporator here and here. So both are having different temperature. So the liquid refrigerant leaving the condenser can be subcooled by passing through a heat exchanger, which is supplied with the saturated vapor coming out from the evaporator. So benefit of doing this is we can see in the pH chart. See here, that is 3 to 3 days. So previously after condensation we are having the saturated liquid refrigerant, but in this case we are having the subcooled refrigerant. So the benefit of that is we are having the more refrigerating effect, so that the whatever the vapor refrigerant that is passing from the heat exchanger are get superheated, and also the liquid refrigerant coming out from the condenser get subcooled. So dual benefit of the using of subcooling. So here again the heat balance, that is heat lost by the liquid refrigerant and heat gained by the vapor refrigerant. So heat lost by the liquid refrigerant is M2 into C T3 minus T3 dash, and specific heat of liquid Cp, and M1 Cp T1 dash minus T1, both are the equal. So mCp delta T is equal to mCp delta T. Okay. So here M2 and M1 taken as different, but actually the mass is same. But in this notation, M1 is the mass of liquid refrigerant and M2 is the mass of vapor refrigerant. So HF3 minus HF3 dash is equal to H1 dash minus H1. So ultimately we are having T1 dash is equal to T3 dash is equal to Tm. So from that, mass of refrigerant that is required for the cooling is 210 Q divided by H1 minus HF3 dash kg per minute. So power required to drive the compressor, that is P1 is equal to Mr H2 dash minus H1 dash by 60 kilowatt, that is equal to this 210 Q by 60. If we put the value of that, then H2 dash minus H1 dash divided by H1 minus HF3 dash kilowatt, and power required to drive the compressor without heat exchanger is this. this power is with heat exchanger while we use as subcooling, and this one is when we are using without subcooling. So, this is the power without heat exchanger and this is the power with heat exchanger. So, excess power that we need is P1 minus P2 kilowatt. So, here we see that the subcooling of the liquid refrigerant by vapor refrigerant, the coefficient of performance of the cycle is reduced even with theoretical loss resulting from the above type of subcooling. There are many actual installation which can be adapted for this process. So, if we consider COP, then COP will be less compared to previous to modification. So, this one is better compared to previous two modifications. Now, next one is subcooling of liquid refrigerant by liquid refrigerant. This is the modification of last system. In last system, we are subcooling the liquid refrigerant by vapor refrigerant, but in this case we are subcooling the liquid refrigerant by the liquid refrigerant. So, the heat exchanger is produced between condenser and expansion valve, and after expansion valve here at 4 dash point, some of the liquid refrigerant is bleeded and that is transferred from the heat exchanger. So, the M2 is the mass that is coming out from the condenser and M3 is the mass bleeded from the liquid passing to the evaporator, and that is supplied to heat exchanger, and M1 is the mass that is supplied through the evaporator. So, here little bit of difference is there in heat exchanger. So, here we can see that in pH chart the 4 dash point is on the saturated liquid. So, the refrigerant leaving through the expansion valve is saturated liquid, no vapor contained inside that liquid refrigerant. In last case, if we see the pH chart, the 4 dash point is in between mix up zone. So, it is in wet vapor region. So, the liquid refrigerant has somewhat amount of vapor, but in this case we are not having any vapor particles inside the refrigerant. So, the 4 dash point is completely saturated liquid. So, here again the heat balance is heat lost by the liquid refrigerant, it is heat gained by the liquid refrigerant from the expansion valve. So, here M2 into HF3 minus HF3 dash is equal to M3 H1 minus HF4 dash. From that we are getting the equation for M3, and refrigerating effect is M1 H1 dash minus HF4 dash, and W is equal to M2 H1 minus H2 minus H1, and COP is RE by W. So, we are having final equation of COP is H1 minus HF3 divided by H2 minus H1. So, if Q tons of refrigerant is the load on evaporator, then the mass of refrigerant, that is M1, required to be circulated through the evaporator, and that is given by this equation of M1. So, this is the mass required into the evaporator, and total mass of M2, that is needed to be handled into the compressor, is this M2. So, this is the total mass of refrigerant required for the system, and from that the power required to drive the compressor is this. So from the equation of refrigerating effect, we see that the mass of refrigerant required in heat exchanger is exactly equal to the mass of flash that would form in the simple saturation cycle. Also, COP of the cycle and power required to drive the compressor is same as that of simple saturation cycle. Therefore, this arrangement of subcooling the liquid refrigerant is of no advantage. In other words, the above method of subcooling is thermodynamically same as the simple saturation cycle. So, this is also not for the best suitable for modification. So, from among these all 4 modification, only third one, that is subcooling of the liquid refrigerant by the vapor refrigerant, is better to improve the COP. The first method is utilized to reduce the mass handling and reduction of size of evaporator, and other two are just utilized to change in the refrigerant. It doesn't affect the components and the coefficient of performance of the system. So this is it for this video. Thank you for watching.